Good morning and welcome to today's class. My name is Mr. Samuel Osinde, chemistry mathematics teacher, Boqol soon. Today I want us to continue from our previous class, which was on structure and bonding. In the previous class, we looked at ionic bonding, and I introduced briefly covalent bonding. So today I want us to discuss more about covalent bonding. And covalent bonding takes place when atoms share electrons. We saw that for a bond to take place, there can be electron sharing, there can be electron lost, which is also gain, or what we call complete transfer of electrons. So today we want to look at what happens when atoms share electrons. Most of the nonmetals, they have a tendency of gaining electrons, but sometimes when they are cornered together in a chemical reaction, none of them is able to give out its electron, and therefore they opt to share rather than give out electrons. So covalent bonding majorly focuses on nonmetals common amongst nonmetals, and this involves sharing of electrons. So they do so to ensure that their outermost energy level has a stable electron configuration. So this one is done in order to achieve a duplet or octet configuration. For covalent bonding, the focus is on the outermost energy level, or the outermost electron, also known as the valence electron. So sharing is majorly amongst the valence electrons. So the valence electrons are the electrons in the outermost energy level. So when you are going to look at some of the structures that are formed when covalent bonding takes place, we are only going to focus on the outermost energy level and not the other energy levels, because sharing takes place among the valence electrons, and you know very that the valence electrons are always situated in the outermost energy level. So this one is common in molecules, covalent bonding. Such as oxygen molecule, hydrogen molecule, chlorine molecule, you have nitrogen molecule, you have water, so it's a molecule, you have the carbon 4 oxide, you have the sulfur, not the sulfur but the carbon monoxide, you also have ammonia molecule, etc. So this one is majorly common in molecules, and when you look at all these molecules, they are made up of non-metallic elements. They are made up of non-metallic elements. So we want to look at some of the common, or how do you draw some of the covalent structures that are formed especially in this molecule that I have stated there. It's also important to note that The focus, as I had said earlier, is on the valence electrons only. So you can see molecules can be formed when you have atoms of the same elements coming together, bonded covalently, or atoms of different elements, bonded covalently. So I want us to look at some of the structures here. I wanted to start with hydrogen molecule. So in hydrogen molecule, we have two hydrogen atoms that are bonded covalently, and you know that each hydrogen atom has one electron, and therefore for the hydrogen atom to be stable, they need one more X electron. But we have said there is no giving electrons here, but they are sharing. So if you have a hydrogen atom with one electron, the outermost energy level will overlap with another hydrogen atom. So this one will give it one, then the other one also brings one, so they share. So you can see now the two energy levels as the two energy levels have two electrons each. This one is from this hydrogen, the other one is from the other hydrogen, and therefore they share. So you can see there is some overlap of outermost energy levels. They overlap, and this space is where the sharing of electron takes place. So you can also represent this using a line, always covalent bond. You can say hydrogen bonded to another hydrogen. So this line here represents one covalent bond which carries two electrons each from the two bonding atoms. The next one which I want us to look is oxygen molecule. Oxygen molecule. The oxygen molecule contains two oxygen atoms. We know that each oxygen atom has 6 valence electrons, and therefore each oxygen atom will require 2 more electrons to achieve the octet configuration. So one oxygen atom, we only focus on the valence electron, that is the outermost energy level. So we are not going to look at the inner energy levels, because sharing takes place amongst the valence electrons only. So you have oxygen, you have to draw one energy level, then you have also another oxygen, there will be some overlap. So this one has 6, this also has 6 electrons. So they bond covalently. When this one brings one electron, the other one brings the next electron. So that is one covalent bond. This one electron is from this side, the other from the other side. So which means now here we have 5 electrons remaining, here also 5 electrons remaining. These 5 electrons are the unbonded, or what we also call the lone pair. Lone pairs. Then the next oxygen gives 1, the other also brings 1. So which means now we have 4 lone pair, 4 unbonded electrons and 4 on the other side. So already in the 2 orbitals that are overlapping, in the 2 energy levels that are overlapping, you have already 4 electrons, and therefore the other 4 you write them as lone pairs. So you will put 2 here, another 2 here. That makes this oxygen to become stable, because now the outermost shell has 1, 2, 3, 4, 5, 6, 7, 8. Then the other 4 also you represent on the other one. This also will have 8. 1, 2, 3, 4, 5, 6, 7, 8. So these unbonded electrons are what we call the lone pairs. They are bonded electrons, the ones which have not participated in bonding. So this one is the oxygen molecule. This is the oxygen molecule, and in terms of covalent bonding, you can say that oxygen to covalent bond another oxygen atom. So the 2 lines represent the 2 covalent bonds. This is one covalent bonding, another one. So that's why we put 2 lines there to represent the covalent bonding. So this is the oxygen molecule. The next one is chlorine molecule, which is also Cl2. We know that a chlorine atom has 7 valence electrons, and therefore each chlorine atom requires 1 electron to become stable. So if you are to draw this, let me draw it better. So Cl, that way. So this one has 7. We are not representing the outermost energy level. This one also has 7. So this chlorine will bring 1 electron. The other will also bring 1 electron. So which means that now all the outermost energy level has 2 electrons, and therefore the remaining electrons, which are now the lone pairs, will be 6 on this side and 6 on the other side. So each one of them will be stable. So the 6, these are the lone pairs, then the other 6. So now each chlorine atom has 8. 1, 2, 3, 4, 5, 6, 7, 8. Octet. 1, 2, 3, 4, 5, 6, 7, 8. So this one is the chlorine molecule, and in terms, because there is only 1 covalent bond formed, you can write it as this, Cl, Cl. So this is the 1 covalent bond which is formed when they share their electrons. So from the 3 molecules, you can see they are made up of atoms of the same element. But sometimes you can have a molecule like ammonia, which is NH3. So in ammonia, you have 3 hydrogens covalently bonded to 1 nitrogen atom. So you know that nitrogen has 5 valence electrons. Nitrogen has 5 valence electrons, and hydrogen has 1 valence electron. Therefore, each hydrogen atom will require 1 more electron, but these electrons are going to be shared. So you put nitrogen in the middle. You know the number of atoms that the number of electrons nitrogen can share are 5. So we have got 3. So you attach 3 hydrogens on the nitrogen atom. So we know that each hydrogen has one. So the dotted one are the hydrogen electrons. Then nitrogen has 5. So nitrogen will bring each one electron. So there will be one covalent bond here, another one here, another one here. And therefore, nitrogen will have some lone pairs here. Because nitrogen has 5, so it has used 1, 2, 3 to bond to the 3 hydrogens. So there will be a lone pair which will be remaining, which is this one. So each hydrogen is now stable because the hydrogen only has one energy level, which means just require one electron to be stable. So this one is stable, and the other one as well. Nitrogen on the other hand will have 1, 2, 3, 4, 5, 6, 7, 8, which is also stable. So in terms of the lining, you can have nitrogen 3 volts to hydrogen. Or you can have, just to make it more simpler, you can have nitrogen. On this side there's hydrogen, there's also hydrogen, then there's also hydrogen, and then you have the lone pairs. You have the lone pairs. So it is important also to know the lone pairs. In the previous examples here, also you have to give the lone pairs which are for the oxygen. Also here you have this. Very important. So we should not forget that. There is also lone pairs here for chlorine. Those lone pairs are very important. Or the other one also as well. So even the lone pairs for nitrogen, you have also to represent them. So this one is this hydrogen, this one is this, and the other one is this. Then the lone pairs are up there, which we were using a cross instead of the dot. So this one is the ammonia molecule. You can see it is made up of nitrogen and hydrogen. So we can move further also to structures like carbon dioxide, which is common known as the CO2. The CO2 is a gas having one carbon atom and 2 oxygen atoms covalently bonded. We know that each oxygen has 6 valence electrons. Hence require 2. Hence require 2 more electrons. While the carbon has 4 valence. Four valence electrons, hence require 4 more electrons. So this means that for carbon to be stable, it needs to form 4 covalent bonds, because each covalent bond entails 2 electrons. So if carbon forms 4 covalent bond with this 4 valence electron, it will be stable. Then for oxygen to become stable, it needs to form 2 covalent bonds, because the 2 covalent bonds will bring 2 more electrons for sharing. And therefore, the CO2 structure So we have the oxygen and another oxygen on the other hand. So carbon has 4, so it will bring 1, this oxygen brings 1, so this oxygen must form 2 covalent bonds for it to be stable, another one, then this one. So it means this oxygen has 2 lone pairs. 2 lone pairs, which is this one and this one. Those are the lone pairs. So this oxygen is stable because now it has got 1, 2, 3, 4, 5, 6, 7, 8. The carbon still has 2 more electrons, so it will bring, the other oxygen brings 1, carbon brings the other one. This also will have 2 lone pairs because it has only used 2. So the other oxygen will also be stable, 1, 2, 3, 4, 5, 6, 7, 8. While the carbon will also have 4 on this side and 4 on the other side. So even the carbon atom will be stable. And therefore, when you write this in terms of carbon, 2 bonds oxygen, also 2 bonds oxygen, then the lone pairs is important also to show the lone pairs, the unbonded electrons in the oxygen atom, which are 4 and 4 on either sides. Carbon has no lone pair because all the 4 has been used for bonding. So basically, covalent bonding might seem very easy, but I've realized with most students that when it's come to arithmetic of electrons, they tend to have so many challenges. So you must first know that how many valence electrons exist in each atom. Then how many electrons does it require to be stable? That one will also help you to know that, for example, if oxygen requires 2 more electrons, then this will be equivalent to 2 covalent bonds, which will make it now to have 4 more electrons, 2 more electrons from the already existing 6, and then becoming stable. There is a certain special type of covalent bond which I also want us to look at. A very special type of covalent bonding in which there are some generous non-metals we have seen that for pure covalent bonding, each atom will donate electron for sharing. But sometimes there are some generous non-metals that decides to give all the 2 electrons that need to be shared. This one always happens in few molecules, whereby the bonded electron, the shared pair of electrons, comes from only one atom instead of the other one also donating. So this one involves special type of covalent bonding in which the pair of shared electrons is donated by one of the bonded atoms. So sometimes you can find for bonding to take place there is need for some sacrifices, and this one always happens, especially when you have got 2 atoms that are bonding and one atom is deficient in electrons, or one atom has fewer number of electrons. You will find that in that case the atom with more electrons will decide to give the 2 electrons to be shared instead of each one of them donating 1. This one is evident in molecules such as ammonia molecule, hydroxonium molecule, CO, SO2, SO3, etc. So these molecules, of course, there will be some covalent bonding, but at least amongst all of them, you will find there is some coordinate bond. It is also important to note that coordinate bond is also called dative bond. It's also important to know that coordinate bond is also called dative bond. So I wanted to start with ammonium ion structure, which is NH4 positive. And I'll also explain why the positive charge is there. In this particular structure, you have got nitrogen and 4 hydrogen atoms. But out of those 4 hydrogen atoms, there is one which does not have any electron. There is one which does not have any electron. So that one we call it hydrogen ion. So there is hydrogen ion which is deficient in electrons, and this is also known as a proton. So this hydrogen ion is coming to bond to ammonia molecule, and it does not have any electron, so it has lost its electron, and therefore ammonium ion is derived from this. You can see this nitrogen has got a lone pair here. So this lone pair are what it will donate to this hydrogen ion to form a coordinate bond or a dative bond. So this one is derived from ammonia molecule, derived ammonia molecule, in which the lone pair in nitrogen is donated to hydrogen ion, donated to hydrogen ion. So the nitrogen atom will now decide to donate its lone pair to the hydrogen ion, forming coordinate bond. So in terms of structure, the 3 hydrogen atoms here, these ones have got electrons, so they are not deficient electrons. So this is the electron, another one, another. Then the nitrogen brings one each. This what we show is ammonia. Then you have the lone pairs there. But now another hydrogen comes without electron and bond on this part, forming a coordinate bond. So the positive charge is because the proton which has come has added more positives, because it has no negative, and therefore the whole molecule will have a positive charge. That is why when you draw this, you must put this and this, then you say there plus, because there is additional proton in the structure, and therefore the net charge of this is a positive. So this is the ammonium ion, which is NH4, there is a plus there. There's a radical. So you can see that in this bond, the hydrogen here has not donated any electron, and therefore the 2 electrons have come from nitrogen. That's why we are saying this is a coordinate bond, because the bonding electrons have been donated by only one atom. So in terms of you will have N, this covalent, another covalent, another covalent, but now the dative we write with an arrow. For the dative bond, must put an arrow, then write a hydrogen. So the arrowed one is the dative bond, which is this one. This arrow shows that the pair of electrons are coming from nitrogen. All of them are coming from nitrogen, and therefore this one is a hydrogen proton. So in terms of line diagram, you can have that as the ammonium ion molecule. The next one is hydroxonium ion. This one is derived from water molecule. The hydroxonium ion H. This also has a plus, and that plus means that there is a proton there, which is a hydrogen ion, which is coming in a water molecule. This is also derived from water molecule. So in a water molecule, we know that it is H2O. And therefore, for a water molecule, you'll have oxygen being the center, and you have hydrogens on either side. So this hydrogen brings one, oxygen brings another one. The other hydrogen, oxygen brings another one. And therefore, this oxygen will have two lone pairs. Because oxygen should have 6 electrons, so it has used 2, 1, 2. There will be remaining 4 electrons. So these two lone pairs is whereby now a hydrogen ion. So the oxygen atom donates the pair of electrons to a hydrogen ion, to a hydrogen ion, which is now a proton. So the proton has no electron, and therefore that is why the oxygen atom decides to donate the pair of bonding electrons. So the hydrogen ion can come and bond here. So when that happens, then this bond is no longer covalent but a coordinate bond, because the two electrons have been donated by one atom. This hydrogen has no electron. So in terms of you can have O, you have H, then you have another H. But this one must be an arrow. Then you have some lone pairs here. Some two lone pairs there. So this is why we say this one is now the H3. Oh, but there's a plus, because this proton comes with more positive charges, and therefore it adds, because it has no electrons, so it is positively charged, it will have a positive charge on the water molecule structure. That's why this charge, and therefore must as well put this and say plus here, because it is an ion. It is an ion. Very well. The next that I want to draw is the carbon monoxide molecule. Carbon monoxide molecule. This one is the CO, so we know that it is CO. Whereby you have one carbon and one oxygen. So the carbon and oxygen. This one has 4 electrons. This one has 6 electrons. The valence electrons. So they will start bonding covalently, where carbon will donate 1, oxygen brings 1. Carbon brings the other one, oxygen brings the other one. Then it means carbon will remain with the 2, oxygen will remain with 4, because they have formed, both they have donated 2 electrons for bonding. So if you represent the lone pairs of oxygen, oxygen will be stable because it will have 8. But what about carbon? Carbon will not be stable. So oxygen will decide to give a lone pair of electron to the bonding space, whereby you have now, so those ones have come from oxygen. So oxygen also we have 2 remaining, which will be represented there, and also the carbon also having 2. So you can see now in this space they have 6 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 7, 8. But the last 2 electrons, which are this one, have been donated by oxygen. Those ones have been donated by oxygen. That's why we say this one is a coordinate bond. That's why we are saying there is a coordinate bond in that structure. So you will have carbon, 2 covalent, 1 dative bond, oxygen. Then of course you'll have the lone pair and also the lone pair. So this last bond is this one, which is a dative bond in which the oxygen atom decides to give a pair of electrons to make sure that the bonding atoms are all stable. So this how coordinate bond takes place. It's also a special type of covalent, but the difference is the bonding electron comes from one of the atoms rather than the 2 donating 1, 1. So I want us to move to the types of structures that are formed out of covalent bonding. Type of structures that are formed out of covalent bonding. So we have covalent bonding structures, because we say that when atoms bond, the bonds can repeat itself and form a structure. So out of ionic bonding, we saw that the structure is called giant ionic structure, which is present in sodium chloride. But what about covalent? So there are 2 structures. One is called simple molecular structures. This one is common in molecule from the name, simple molecular structures. Then 2, we have giant covalent stroke atomic. So some books will talk of giant atomic structures. These are the 2 possible structures that you can derive from covalent bonding. So we want to look at some of the properties or some of the common substances that have simple molecular structures and the ones that have giant covalent structures. So let's start with number 1, simple molecular structures. So this one is common in molecules such as CO2, hydrogen, nitrogen, oxygen, chlorine, we also have water, those are molecular structure, etc. So simple molecular structures, or rather molecular structures, is common in water, most molecules, the ones we have drawn. Then we have got, most of these are gases, so most are gases or liquids at room temperatures, So most are gases or liquids at room temperatures, most of these. So we are seeing a trend in these substances that when you look at them, they will exist as gases, and there's a reason for that, why they will exist as gases or solids or liquids rather at room temperature. So the reason is because they have low melting and boiling points. They have low melting and boiling point, and this is because although the atoms are bonded covalently, but the intermolecular forces, because we have said they are mostly molecules, we have what we call the intermolecular forces. So this is because they have weak intermolecular forces of attraction. So I'll dwell more on this. The intermolecular forces of attraction, there are two in number. So there are two intermolecular forces. One is called the weak van der Waals. The weak van der Waals, and another one is called hydrogen bonds. So the weak van der Waals in common in molecules like oxygen, CO2, hydrogen, chlorine, iodine, etc. But the hydrogen bonds, these ones are found in water, in ethanol, and most alcohols. So between the two intermolecular forces, hydrogen bonds are much stronger than the weak van der Waals forces. That's why in the normal room temperature you will find carbon dioxide as a gas, but water is a liquid, because the hydrogen bonds in water are much stronger than the weak van der Waals forces of attraction. So a hydrogen bond hydrogen bond is an intermolecular force in which the electropositive, the electropositive hydrogen atom So this one is common in water molecule, whereby we have got hydrogen and oxygen. So common in water molecule, the H2O. So you can have a water molecule. This hydrogen is partially electropositive and this partially electronegative. So this is just one molecule of water. Then you have another molecule. Electronegative. So there will be some, so this is one molecule, this is also another molecule of water. So there will be some attraction between this electropositive hydrogen and electronegative oxygen. So they will attract to each other, and this one is what we call the hydrogen bond. So it is an intermolecular force because it links two molecules. This one molecule H2O, there's another one. But there exists some attraction between the electronegative oxygen and the electropositive hydrogen, forming some intermolecular linkages called hydrogen bonding. This one is much stronger than the weak van der Waals, which is present in CO2 or iodine. So if you have iodine molecule, another iodine molecule, so this is one molecule, this is another one. Those are iodine molecules, and there are some forces, the dotted ones, which are joining them together. So these forces are what we call van der Waals. Van der Waals. These van der Waals are much weaker than hydrogen bond, and that is why the water will exist as a solid, while most of these will exist as gases. So I want to stop there, and in the next class we shall look at the giant, the physical properties of molecular structures, and also we shall talk about giant covalent structures. This one, just to say a few, this one is common in silicon, 4-oxide, diamond, so having giant covalent, and graphite. So these three, we shall also look at why these ones have giant covalent and the other one have simple molecular structures. Thank you very much. I hope you enjoyed the lesson, and let us meet in the next lesson. God bless you.